In this second video, we're going to derive our first exciting property of complex functions. We will see how the existence of a complex derivative gives rise to the Cauchy-Riemann conditions that relate the real and imaginary parts of a complex function, and we'll be using these relations a lot throughout the rest of the course. As a quick recap of the previous video, we looked at how to define partial derivatives of real multivariable functions. In particular, we defined these as limits for changes in one of those multiple variables. We then found that for some complex function, its real and imaginary parts u and v can be thought of as real functions of the variables x and y. And lastly, we looked at various ways of visualizing the action of complex functions. After watching this video, you should be able to derive the Cauchy-Riemann conditions for differentiability of a complex function. And you should also be able to test a complex function for differentiability using these Cauchy-Riemann conditions. Let's begin.
We're going to be dealing with complex differentiation. We want to be able to find the derivative of some complex function f of z. And in this video, we're going to be using partial derivatives of real multivariable functions, namely u and v, to write down the complex derivative of a complex function. First of all, let's define what we mean by complex differentiation. By analogy with the real case, we define the derivative of the complex function f of z as, so as before, it's going to be a limit. We denote it df by dz. We can also use notation like f prime of z or f superscript 1 of z. This is going to be defined as the limit as the change in the complex number z approaches 0 of the variation in the function divided by the change in the input parameter. And we can also write this as the limit of delta z tending to 0 of the function value at the point in the complex plane z plus delta z minus the value at z, and then divided by this small change. And we can draw a picture to understand what we mean by delta z. In the complex plane, we have the real part x, the imaginary part y. Let's suppose that we're interested in finding the derivative at some point z. To do that, we'll be looking at the function value at z plus delta z. So there's this distance, which we can label as delta z, and we can also write this as the sum of some real increment delta x and some imaginary increment delta y. We note that we can write this small change in the complex parameter z as a sum of a small change in the real parameter plus a small change in the imaginary part. Now, unlike in the real case, where we had delta x tending to 0 either from the right or the left on the real number line, in this case delta z can go to 0 in infinitely many ways, because within the complex plane there are an infinite number of ways to approach that single point z. So I'll write that down. Unlike in the real case, where delta x approaches 0 either from left or right on real number line, here, delta z can approach 0 in infinitely many ways. So here are two examples of possible approaches. For example, first of all, we could consider setting the variation in y equal to 0, and then let delta x approach 0. And that's an approach parallel to the real axis. We can draw a picture. We have the real part, the imaginary part, and let's say we want to evaluate the derivative at some point z, and we're going to, in this case, be considering delta x approaching 0, but there's no change in the y component. The other approach we're going to consider is where instead we set delta x equal to 0, and now let delta y approach 0, now parallel to the imaginary axis. And again, we can draw a little picture to see what this means. This now means that for the same point z, we're now approaching parallel to the y-axis. So delta x equals 0, and it's delta y that's approaching 0. When we talked about the differentiability of a real function, we insisted that the limit had to be independent of whether it was approached from the right or from the left. Now, given some single-valued complex function, for it to be differentiable, these different approaches that we've got on the page here must give the same result. In other words, the complex derivative is unique. I'll write that down. Given some single-valued complex function f of z, I'll also briefly note here I've specified that the complex function should be single-valued. In topic 4, we're going to be dealing with multi-valued functions like the complex logarithm, and we'll see the consequences of that in the next topic. Given some single-valued complex function f of z, then to be differentiable, these different approaches must give the same result. In other words, the derivative has to be unique. Now let's look at what we need when calculating this limit. Looking at the numerator, we have delta f is f of z plus delta z minus f of z. F of z plus delta z, well, we know that we can separate this increment delta z into real and imaginary parts. And we also know that we can think of a complex function of a single complex variable as a complex function of two real variables. So we can rewrite this as f of x plus delta x and y plus delta y. We also know that we can split up the complex function into its real and imaginary parts given by real functions u and v. So we can write f of z as its real part, u, and its imaginary part, v, that we saw in the previous video. So combining these two lines, we then have that f of z plus delta z is given by u of x plus delta x, y plus delta y, plus I v lots of x plus delta x, y plus delta y. That means that our small increment delta f, which is f of z plus delta z minus f of z, this is given by, and substituting in from above, so the first part is from f of z plus delta z, this second part is from f of z, that's the real change, and the imaginary change is given by this. So this first term, which is the change in the real part, we can denote as delta u, and the second part, the change in the imaginary part, we can denote delta v. Now we've got this expression for the numerator of the quantity we want to take the limit for. We can now write for our complex derivative df by dz is the limit as delta z tends to 0 of delta f by delta z, and this is now the limit as delta z tends to 0. So the numerator, we know we can write this as delta u plus I delta v, and similarly we can rewrite the denominator in terms of its real and imaginary parts. Now how do we take this limit as delta z approaches 0? Well, we can compare what this yields for the two different approaches that we described above. Let's compare what this yields for the two approaches above. The first approach, if we write down the limit as delta z tends to 0 of delta f by delta z, for the first approach we assume that there was no change in the imaginary component of delta z, and that means we can write the limit solely as a change in x. So this becomes the limit as delta x tends to 0 of delta u plus I delta v over delta x. So we've effectively set delta y equals 0 in the expression at the top of the page. Note that delta z is purely real. We can split this up into the limit as delta x tends to 0 of delta u by delta x, and then I times the limit as delta x tends to 0 of delta v by delta x. Now, because u and v are real multivariable functions, and delta x is a variation of one of these variables, these are the definitions of the partial derivatives that we discussed in the previous video. We can therefore write this as du by dx plus I dv by dx. The second approach that we looked at above, we now write that the limit as delta z tends to 0, again of delta f by delta z. And this time we consider the case where delta x equals 0 and now it's delta y that's approaching 0. So we now have delta u plus I delta v divided by I delta y. And I'll write on the right hand side that here delta z is now purely imaginary. With some shuffling around of factors of I, we can again identify some partial derivatives, and we obtain minus I du by dy plus dv by dy. As mentioned above, for the derivative df by dz to be unique, it must be independent of the approach. So these limits must be the same. So we can equate these two expressions that I'll label with asterisks. So we must have that du by dx plus I dv by dx equals minus I du by dy plus dv by dy. I'll make the first term on the left a little bit bigger. Okay, so this statement must hold in order that our derivative be unique. Complex numbers are equal when both their real and imaginary parts are equal. Complex numbers are equal when both real and imaginary parts are equal. And, well, the real parts are easy to spot. So the first equation, if we match real parts, is going to be that du by dx on the left-hand side is going to have to equal dv by dy on the right-hand side. And then if we match imaginary components, on the left-hand side we have dv by dx, and on the right-hand side we have du by dy. These are the Cauchy-Riemann equations, and they're extremely important, so I'm going to put a red box around them. And it's worth remembering them. Cauchy-Riemann equations. To hammer home the point, these are the Cauchy-Riemann equations that a complex function given by f equals u plus iv must satisfy to be differentiable. And as a reminder, u and v are real functions of two variables, namely x and y. And these equations, these Cauchy-Riemann equations, can be used to relate u and v. This means that if you give me u of x and y, then I can figure out which v makes the resulting complex function differentiable. We've shown that the Cauchy-Riemann conditions are necessary for a complex function to be complex differentiable. And it turns out that together with the condition of continuous partial derivatives, so together with continuity of partial derivatives, these conditions are also sufficient. We just saw what the consequences are of demanding that df by dz exists. You can also look at things the other way around. So conversely, if the Cauchy-Riemann conditions hold for functions u and v, and partial derivatives are continuous, then df by dz exists. A final point I want to make here is that we insisted that the approaches along the x and y directions gave the same result to get these Cauchy-Riemann conditions. And in a way that means that we treated delta x and delta y as a basis for delta z variations. You can also go about parameterizing your approach using a line with some gradient m, then insisting that your derivative be independent of m. You also get these same Cauchy-Riemann conditions. To finish this video, I'm just going to go through a couple of examples to show how we can use the Cauchy-Riemann conditions to check differentiability of a complex function. So let's first consider f of z equals z. Now we know that we can write this as x plus iy. That means that we can identify the real part. The imaginary part is y. Now the first Cauchy-Riemann condition was that du by dx is dv by dy. Du by dx is simply 1, and dv by dy is 1. So this first condition holds. The second Cauchy-Riemann equation was du by dy equals minus dv by dx. Du by dy is 0. dv by dx is 0. And so the second Cauchy-Riemann condition also holds. Therefore, f of z equals z is indeed complex differentiable. Next example, we can think of z squared. And we can again expand this in terms of x and y as x squared plus 2i xy. And then we've got iy times iy, which is minus y squared. We identify the real part as x squared minus y squared, and the imaginary part as 2xy. Now the first Cauchy-Riemann condition, we need du by dx, which is 2x, and we need dv by dy, which is also 2x. So that's valid. And the second Cauchy-Riemann condition, we need du by dy, which is minus 2y, and then we need that to be minus dv by dx, which is 2y. So that also holds. Now what is the complex derivative of z squared? Well, we know that if we pick an approach where delta y is 0, then we can write this as du by dx plus I dv by dx. Du by dx is 2x, dv by dx is 2y. So this is simply 2z, which is exactly what we would expect from differentiating a real function like x squared, we would get 2x. The same holds here for z squared, we get 2z. A final example, let's consider f of z is the imaginary part of z, in other words, y. Here u is y, and v is 0. The first Cauchy-Riemann condition, du by dx, is 0, dv by dy is 0, so that holds. The second Cauchy-Riemann condition, du by dy is 1, and minus dv by dx is 0. This is not true. So the second Cauchy-Riemann condition doesn't hold, and therefore f of z is the imaginary part of z is not complex differentiable. There are a lot more examples of using the Cauchy-Riemann conditions in the third problem sheet, so you'll have lots of practice there. I'm going to finally note that the usual rules for derivatives hold for complex differentiation. And what I mean by that is things like the product rule, the quotient rule, and the chain rule. And I'm not going to prove these, but you can look in some of the books suggested in further reading on the resource list for rigorous proofs of this. That's the end of this second video of topic 3. As a quick recap, we saw how the existence of a well-defined complex derivative enforces strong conditions, the Cauchy-Riemann conditions, that relate the real and imaginary parts u and v of the complex function f. And in the following videos, we're going to see how amazingly restrictive these simple relations are. Thanks for listening.